This sample problem deals with a person hitting a tennis ball, and we're going to be interested in calculating the change in momentum, the impulse, and calculating the force applied to the tennis ball. And we'll talk about some assumptions that are being made here. So Holly is serving a tennis ball, 0.12 kilograms for the ball, and we're going to take this physics problem to describe a situation where the ball leaves the racket horizontally. We're not going to be worried about vertical motion in this problem, just dealing with horizontal motion. And the speed the ball leaves the racket with is 45 meters per second. After the contact with the racket has finished, the ball has achieved 45 meters per second. We're going to assume the ball was momentarily at rest before the racket hit the ball. Holly threw the ball vertically upward, and at the top of the ball's motion, when it was at rest, not moving horizontally, not moving vertically, there the tennis racket hit the ball. The racket, just give you some more data that you decide what to do with. The racket has a mass of 3 kilograms and a length of 0.7 meters. Important data here, the ball was in contact with the racket for 0.06 seconds, is what I'm claiming in this problem. So we want to calculate the impulse, then we want to calculate the average force of the racket on the tennis ball. Well, you read through the problem a couple times and you make a simple sketch of what's being observed here. So our ball is leaving the tennis racket at 45 meters per second in the horizontal direction. And ask a question, is the momentum of the ball conserved before and after its collision with the racket? And the answer is no. The velocity of the ball was 0 at the top of its motion, 0 vertically and 0 horizontally. The toss of the ball by Holly was straight upward, and at the top of the motion, when the velocity is 0 in both horizontally and vertically, so that was 0. Before or after the collision, the ball has some velocity. So momentum is mass times velocity, so no, we don't expect the momentum to be conserved. And it's not conserved because there was an external force acting on the ball, the force of the racket on the ball. So in that situation, momentum is not conserved. So the racket force is to the left, pushes the ball horizontally. Gravity is also in play here. It pulls the ball downward, and most likely, certainly, there's a force of friction acting on the ball while it's in contact. So we're going to make some general comments about the vertical direction with gravity and friction later, but that'll come later. The key part is horizontal. So how do we calculate the impulse? Impulse is change in momentum. Well, mv after minus mv before. That's the change in momentum. How do we calculate the impulse? Well, you know the mass of the tennis ball. We're given the velocity after, 45 meters per second. And I've been trying to convince you the velocity before the collision is 0. So there was no momentum initially. So our impulse here is 5.4 kilograms meters per second. And impulse has units of mass times velocity. And notice that we did not pull into the calculation the mass of the tennis racket or the length of the tennis racket. That was extraneous data that you had to ignore to work the problem. So there's the impulse. Then thinking about some of the concepts here, does gravity act on this ball? The answer is yes. This is occurring near the surface of the earth. And why didn't I talk about the impulse given to the ball by gravity? Well, I'm working this in the horizontal direction, and that was the data I was given. I wasn't given any velocity in the vertical direction, and let's perhaps check for ourselves why that's not too crucial anyway. Let's remind ourselves 5.4 kilograms meters per second. That's the impulse in the horizontal direction. So let's talk about the force of gravity for 0.06 seconds. If we imagine that there was no friction on the ball during the time of collision, that's a bad assumption, but If there was no friction, then we have vertically acceleration due to gravity. We can find the velocity after the 0.06 seconds has elapsed, and that turns out to be 0.589 meters per second. So in doing the impulse in the vertical direction, the y direction, vertical, we would have 0.12 kilograms at mass times the velocity in the vertical direction after the 0.06 seconds. This is no friction case, it's just a hypothetical. I have 0.07 kilograms meters per second. That's much less than the impulse in the horizontal direction, so that's one reason to ignore it. Also, most likely the ball is not dropping towards the earth during the time of collision, the 0.06 seconds. There's going to be notable friction between the racket and the ball, and most likely the racket is basically going to keep the ball in place in the vertical sense. The ball is not going to be dropping towards the earth. Friction is going to keep the ball in place on the racket. So just a horizontal problem, not worrying about the vertical numbers. Okay, what about the force of the racket on the tennis ball in the horizontal direction? I'm not going to try to calculate the frictional force in the vertical direction, but what about the average force during this collision? I say average because when the racket just starts to touch the ball, there'll be a very slight force on the ball. At the midpoint of the collision, there'll be maximum force, and then as the ball leaves the netting of the racket, the force of the racket on the ball is going to decrease. So the force is variable, but we can calculate the average force. And average force times the time of collision, delta t, is the change in momentum. We found the change in momentum earlier, so I divide by 0.06 seconds, and I come up with average force of 90 kilograms meters per second squared. Why did I change that to newtons? Well, in Newton, the force in newtons is mass times acceleration. And we see here our units are kilograms, that's mass, times acceleration. So 90 newtons of force is the force the tennis racket applied to create the 45 meters per second of velocity of the tennis ball off to the left. So if you'd like to look at some of my other YouTube videos for physics and astronomy, I have them organized by categories, by topic, on my simple website, gpclements.com. There's an annotated list. The annotated list has the title of the video, how many minutes long the video is, a description of the video, and then, most useful, it has a direct link to the YouTube video. You don't have to search on YouTube to find the video you're interested in. You browse my topic list and click on the link that's there, and you're watching the video right away. All this content is free. You're not allowed to sell it, but you do not give me your name or your email address, anything. It's all free, and I don't collect anything. I don't put cookies on your website, on your computer, so hopefully you'll be good to go. Keep working physics problems. Ask your instructor when you have questions.